Hi, my name is Bill Fortney, and thank you for hanging in here in this series on probability and statistics for engineers. It's an essential skill for you to be a good engineer, so I thank you for staying here with me. In this video, I'm going to review real quick, and then you're going to look at how do you calculate specific probabilities when working with data that's normally distributed. Okay, so we started off realizing that, okay, as engineers, we need good information, good data to make decisions. And to do that, we need to ask things, what can I expect from you? Once we know, then we can make the decisions that we need to make. But it's hard because there's variation in everything, and we need to know what to expect from all possible samples, not just the ones we have, and statistics can help us with that. And so then we learned that every number that we collect is a random variable. Random variables follow predictable patterns described by their distribution, and distributions tell us the likelihood, the probability of getting different values of a random variable. And a distribution is described by its shape, its central tendency, and its spread. And then we saw that with the normal distribution as an example, where the shape was bell-shaped, the central tendency was average, the spread was standard deviation, and the probability of getting a value was described by this mathematical function. Now, I didn't say, but how did they come up with that? That's part of the study of statistics, where they have studied all this, modeled, and understand how phenomenon work, and all kinds of mathematical proofs showing that these things hold true when all of the assumptions are in line. Okay, and so then we saw the video where, wait a minute, like how can things in the real world follow a pattern if they're random? And so we saw the video specifically about the normal distribution illustrated through the Galton board, and then we brought it into the factory, where the whole idea, there's more paths leading down the center than there are the other paths. And so things seemingly random in the world, the numbers that we're taking, parts going through our factory, can in fact fall into a predictable pattern, the distribution, and statistics has studied those and quantified them. And so we can't tell where one is going to be, but we can know what the pattern is, and that helps us a lot. So we said, okay, let's pull it together. If the process is stable, we'll see what that really means. Then the values that we're taking, the measurements we're taking of the ultimate or whatever, are random variables. They follow, they behave in a predictable manner described by the distribution. So we said, great, here's what we're going to do. There is a population. We used our factory as an example. There is a population. And let's just, for now, we're saying we know that it follows a normal distribution. So it's got a mu and a sigma for central tendency and spread. And parts are coming out of that, and they are random variables following that distribution. We're going to take a sample, and we're going to calculate the sample average and sample standard deviation in order to estimate the population parameters. We now can use the mathematical functions that we know about the distribution to predict what we can expect for ultimate. And we use the example, let's say the minimum that we could allow was 78.58. We wanted to see the chance of going below that. We could come to the normal, pick this point, use that function that I showed you. We're not going to have to use it. There's tables, and see what that probability is. And so we now have a very good way to say, what can I expect? Then we went and looked a little bit more detail to help you understand average and standard deviation. We said standard deviation is like wiggle. And so we use these three examples to show you three sets of factories, if you will, three different factories, one operating at a standard deviation of 1, one operating at a standard deviation of 2, 1.5, all with the same average to see what that would look like. And then I gave you this warning where I said, look, all of these have the same average and standard deviation. You would never know it unless you looked at it. These do not represent our factory. They don't represent the population because the population is changing. It's like acting as one factory here and another factory up here, and the average never describes it. We're going to see when we talk about real world data. That's something we have to look for. But for now, it was just the warning. You need to look at the data before you use a statistic. So then the last thing we did is brought in the normal distribution to help us see actual percentages to know what we can expect. And we started with this showing that with the normal, the probability of getting a value is based upon how many standard deviations you are away from the mean. So 1 standard deviation, 68% of the parts are going to fall within. 2, 95, 3, 99, and 0.1%, 3% are going to fall below. That tells us a lot. And so we then put that in an example of our process with an average of 81, standard deviation of 1. We take a sample, get the sample average and standard deviation to estimate these. And then we said, look at how much we know now. We now know that 99% of the time, we're going to go between 78 and 84, plus or minus 3 standard deviations. That's a lot of information. 0.13% will be below 38. Then we also saw that each of these areas right here, we can calculate the probability of falling in there. So 2.5% of the time, we're going to be in here. 2.5%, we're going to be up there. And then we put that in the context of, we said, okay, we're making 10,000 parts. How many are we going to have in each of these areas? And then we said, okay, 10,000 a little is hard to see graphically. Let's look at 1,000. So we looked at this, the same percentages, we turned it on its side. There's plus and minus 3 standard deviations. And then we saw that, you know what? We can know how many parts we're going to see in each of those areas. So like plus or minus 1 standard deviation, we're going to see 341 parts in here. Now, what are they going to look like in that range, those 341? They're just going to be randomly falling within there. And we actually went, especially these last 2 ranges, we counted, and sure enough, what they said was going to be there is what was really there. And then one of the things we highlighted here to put on your radar is, now, think about this. What this is saying is the average is not the whole story. We're used to calculating an average and calling it the number. It's not the number. We can reasonably get any of these numbers in this range. So the average isn't telling us the whole picture. We've got to consider the distribution and what is it we need to know in order to make our decision. And then we said, okay, let's bring in the standard deviation to see how it affects. So we looked at the standard deviation of 0.5, 1, and 2. And we saw that the larger the standard deviation, the wider our range is. The wider net we have to cast to say, what can I expect from you? Right down here, what can I expect? I've got a pretty tight range that 99% of my value is going to fall within. Whereas down here, I've got to go way out to get that same level of confidence of how low is my number going to be before I'm pretty sure it's not going to go past that. Pretty sure meaning 0.13% if we go 3 standard deviations. And then we looked at the graph to sort of show what those looked like. And then we made 3 points on this. 1, the impact of standard deviation. Number 2, the reasonableness of getting any number in the range. So if this was our distribution, I tell you the average is 81. It would not be weird for me to get a 75. Now imagine I say to you, dude, what are you doing? I thought you said the number to use was 81. See what I mean? So we're used to that average. We have to consider the distribution and give ourselves or other people an idea of the variation, because all of these numbers in this range are reasonable. So average isn't the whole story. When we're making a decision, when we're reporting, we need to consider the variation and the distribution. Okay, so that's review. Now, let's get on and start looking at actually working with the normal distribution. We saw this before. Here's a normal distribution. It's symmetric. The greatest probability is here in the middle. It tails out. We saw that the whole thing is 1. We can subtract to get other probabilities, and this is the function that describes it. But we don't have to do that because we have tables like this. This particular table is giving us the probability of here back. What's it doing? It's giving us the probability of getting a value less than x. I know that says z. You'll see why in just a second. From a process with a normal distribution, mean of mu, and standard deviation of sigma. Now, what's z? Z is the number of standard deviations away from the average. So the value we want minus the average divided by the standard deviation. The number of standard deviations away from the mean. So let's put it in context of an example, the same one we've been looking at. We take a sample, we have 81 and 1, our sample average standard deviation, estimating the population. And now statistic will tell me exactly what I want to know. So the minimum on the standard is 78.58. We've been seeing that. Now, what's the chance of making below that? I can tell you that. Probability of x less than 78.58. Let's calculate my z value. X, 78.58, minus the average, 81, over the standard deviation is minus 2.42. So what I want to know is less than 2.24 on the standard normal. That's what this graph is. It's the standard normal. It's the probability of a z value. We got this right here. So I come over here to 2.42, 0.0078, or 0.78% of the time. Is that a lot? Well, I don't know. It depends on your decision. It depends on what's writing on it. The statistics is just giving you information in order to make the decision of what you need to do with the problem you're solving. Okay, let's look at another one. What's the probability of getting one greater than 83? Same thing here. I want the probability of greater than here. I calculate my z value. It's 2. And I am going to value of 2, so a greater than 2 is the same thing less than minus 2. So I can still use this same chart. I'm going to come down here. It's 0.0228 or 2.28%. Okay? Now let's work one more. Probability greater than 79, less than 83. So in between 79 and 83. So here's what I'm going to do. I'm going to solve it on this. So that's going to be 1 minus the green area, probability greater than 83, minus the purple area, less than 79. Remember, 1 minus the whole is what's left. That's this area in between. So probability x greater than 83, we just worked. It's 0.0228. Probability less than 79, same z value. And we subtract those, it's 99.54. Now wait a minute. 99.5 ports will be within 2 standard deviations. Yeah, z is 2. That sounds familiar, doesn't it? Yeah, that's where this came from. That's where these probabilities came from. They came from this table. Someone just calculated them for you. But you see the power now of what you know, and this is so convenient. So in practicality, a lot of times when someone's not going to jail, when someone's not going to die, people use 2 and 3 standard deviations regularly. Now, how do they know which one to use, 2 or 3? It all depends upon how certain they need to be. How big a deal is it if you go below what you've calculated? What's going to happen? Statistics can't tell you that. Your judgment, your knowledge of the situation, your knowledge of knowing the impact to your design or to whatever problem you're solving is going to have to tell you that. And you've got to make the decision of, okay, what level of confidence do I need so I sleep well at night that I've made a good decision? That if I get one of those weird points that falls below what I'm talking about, what's going to happen? This is going to happen. It's not a big deal. That means we're going to get one defective part in every 200,000. That's okay. Does that make sense? The statistics is giving you information, and you're going to have to pick, okay, do I want to go 3 standard deviations? We're going to learn in some situations, we're going to go more than 3 standard deviations. If we're going to jail, I'll tell you what I'm going to do is I'm going to go 7 standard deviations. You're going to see why a little bit later. But this is giving you the information that you need to answer the questions to solve the problem. So let's go back to where we started. We had these measurements for the bolts. we wanted to know what can we expect for the ultimate coming out of our factory. And we wanted to know what number to use for our decision. We figured we learned we can't use the minimum because that's just for this sample. We don't care about that. We care for all of them. We were stuck here. But now we know that our solution is, if we know or we can assume the distribution, you'll learn how to do that, that we can use this sample data to estimate the population parameters. Then we can use the probability function for that distribution to predict what will happen. So a huge step forward in terms of having information that we need to make solid engineering decisions. So now I want to give you a chance to try, okay? Now you should have a normal distribution table like this one. There's going to be a link that you'll be able to get that. It's a little different than the one I was using earlier. I added down here at the bottom, this one goes to -4. You can see the probability. I added z less than -5. It's 287 e to the -7. And then a -6, 9.9 e to the -10. And then z -7 is essentially 0. So it has a few more numbers on there. It's got a reminder here how to calculate z. It's symmetric. So you try these next problems, and what I'll do is I'll give you the problem, pause the video, try to solve it, and then I will go through it just so you can see to make sure you didn't miss anything. Okay, so here's the first one. The same problem from the beginning. And so you calculate what is the chance of having a part less than the standard. So the probability of X less than 150,000. So go ahead, pause the video, work this one out, and then restart it, and I'll work it. Okay, so here's our problem. There it goes. So here's what we've got. Probability of X less than 150,000. You see we've got our average here. There's our standard deviation. I calculate my z value. It's -2.71. So I need to go to the table and find z, probability of z less than -2.71. I go 2.71. It's 0.036. Oh, oops, sorry. 0.0336 or 0.034. There we go. So 3.4 in 1,000. So that's the probability. Again, if we're talking about going to jail, that's not acceptable. 3 parts in 1,000, that's no good. Okay, cool. So now here's another one. A little bit harder. You're going to have to think a little on this one, but just follow the same process and it's going to come through. If you had a knob that you could turn and increase the average. So our average is right here, right now. Standard deviation is not going to change. Where would you turn the average to make sure that your manager doesn't go to jail? To make sure that you do not produce parts less than 150,000. So think about it, try that one, pause the video, and then turn it back on, and I'll solve it for you. Okay. So we're going to do the same thing. We want the probability X is less than 150,000. The only difference is we have 150 right there, and we don't know what the average is. That's what we're trying to find out. So I set it up. So I say 150,000 minus X over the standard deviation equals, and I got to come up with a z value. So I'm going to look at here, and I'm like, dude, I'm going with 7 because I don't want there to be a chance of my manager going to jail. And so I put in a 7 right there, solve that algebraically, and it comes to 160,346, which, if you remember, the very beginning, I told you if I had a knob, I would turn it to that. Well, you now see where I got that number. And that's what people really do in industry. I showed you this chart, real bolts that we had bought from McMaster. We tested them, and you see they're way up here. Why are they so much larger? Because they did the math. They looked at their processes, they saw the amount of variability, and they said, look, here is where we're sitting it to make sure that we don't go below 150. So you see, These kinds of things are used all of the time when we are gathering data to make decisions in engineering. And you've got the foundation to be able to do that now. You see how to calculate the probabilities. So, why engineering statistics? Because we need good information to make a decision. There's variation in everything, so we have to take more than one. We're going to take a subset, a sample from the population. We will use that to estimate population parameters, use statistics, in order to be able to have a good idea of what to think. Okay, so the next step is going to be, okay, how do we really do this in the real world? Because there are some complicating factors in the real world that make this difficult. But you have the foundation now, the conceptual framework, if you follow along with all this, and the ability to know how to calculate probabilities from the normal in order to deal with that. So that will be the next session in this series.